Hi, my name's John Joseph. We're asking for investment, and what we're really talking about here is a new type of invention. We have invented and patented a new type of light source, and that light source is infrared. It has really high power and extremely high bandwidth. And we are applying it to 6G technologies, and you'll see why after I go through this. But basically, we're asking the question, why, what is 5G and what could 6G be? It's much faster, it uses less energy, costs less, should cover better, which 5G didn't do from 4G. So we are delivering new 6G emitters for sale to product developers here at the end of this year, and we're asking $8 million. Next, please. My name's John Joseph. I'm the CEO, and I lead an elite team of scientists that worked with me at Sandia National Labs over 30 years ago in a number of areas which basically produce the devices for fiber optic communications today. We're using a similar laser to that, and I'll describe that here now. Let's go to the next, please. So this new light source, as you can see on this finger here, that small chip, there's 20,000 of those chips produced on a 4-inch wafer. That chip has 37 lasers on it. All of these lasers produce enough power to go 2 miles distance at it with a actually this chip is tested over 25 gigabits per second with zero errors. And this is very unusual. It's a new type of architecture for a photonics chip. It basically takes all of the beams of the different lasers, and it sums them with a micro-optic process that's wafer scale. So we can virtually produce that chip for $1, and it is the enabling technology that can send multiple gigabits per second over long distances. Now, the other interesting thing on the patents is that if we shift the micro-optics and X or Y, what we can do is end up with an interesting configuration where we can have multiple chips on the same beam. And this is the proof of that over here. We have 3 chips, and all of those, if you look back through the projection lens's focal point, you will see that 7 millimeters behind this chip, all of these chips are all on the same beam. So that means we can multiplex these at different wavelengths and or different amplitude modulations. So that gives us the ability to put hundreds and hundreds of gigabits per second on a single beam with very high power. Now, the other thing that we can do is shift this micro-optic slightly to the left or right, and what it will do is passively align that beam to a different direction other than the incident angle. So we can actually form an array of arrays like I'm pointing out here, and if we sequence through these chips, we can actually move the beam and direct it non-mechanically, which is a huge benefit for free space optical communications. Typically right now, free space optical communications have to have expensive, heavy gimbals that move the beam around. So we are producing a new high resolution chip in phase 2 of the National Science Foundation project, and we were successful in that first phase 1. Next, please. This is just kind of more data on how this works. All of the beams overlap at some point, and at that overlap point, all of the intensity is very nice and high and uniform. And that's what we project into the far field. Next, please. And this is more indication that what we can do with that, how small it is, and this is actually showing that we can form the beams to whatever. This is the hexagon that you saw that we made out of the laser, and that's what's projected into the far field, and we can sequence through and move the beam. Next, please. These are beam calculations coming straight out of the chip. Next, please. Sorry about the data. Next, please. So there's many use cases for this module, and the 5G backhaul is where we're applying it now with our first product, which I'll show you here in a second. There's all kinds of different use cases for this, including mobile vehicle-to-vehicle networks, data center, low loss connections, many types of things that can change with this new technology. There's too many to go into right here. Next, please. So what we are delivering this year at the end of the quarter is we are developing these boards, and these boards we put into a system and proven the system works well. So now we're going to sell these development boards to equipment manufacturers for very high-speed wireless, optical wireless equipment. Next, please.
Hey, John, 30-second
Yes.
warning.
Okay, next, please. So this is what we've shown. We put one of these chips into a system, and that system we put on 2 buildings at a local college at over 100 meters distance, got 10 gigabits per second upload and download. And we are now in our next version of that, which has automatic alignment and all kinds of cool networking capabilities. Next, please. There's the use cases for this first product, which is basically getting across rivers and highways and train tracks, which this is ideal for. And we talked to 100 customers and they all need this really badly. Next, please. Space is the big one. We've got multiple partners right now that is looking and evaluating our devices for celestial links and in space, satellite, and different partners looking into that, whether it's ground to earth, earth to earth, or LEO to LEO satellites. Next, please. And the big one is the smart pole. We are manufacturing a smart pole, which we will have other manufacturers put the actual electronics and cell type devices through, but we're having a conference on this, on 6G conference, to allow us to conceive and build this new smart pole in the best possible way for third party connections. Next, please. Lots of traction. We've got a DoD phase 2. We got an overachievement status in it, and that was with the Army. We're in phase 2 on schedule and on budget. We've got another National Science Foundation phase 2 coming in, and we have lots of production, wafers grown, chips made. We've raised $4 million to date. Next, please. Next, please. We're asking for $8 million basically for operations, and something's recently changed with us, the ability to make a production facility. And if you're interested, we'd like to talk to you. Next, please. Thank you very much for the opportunity, and be glad to answer any questions.
I'll go. Thank you, John. Exciting technology. From a range standpoint, can you speak to data rate versus range?
Yes. So RF has a problem. 5G millimeter wave only goes a few hundred meters because they go to a higher frequency. That depends on power and divergence angle. We have huge amounts of power and virtually unlimited because of this new architecture of the chip. So right now we are expecting to go easily 5 miles with our chip technology, but there has been some recent modeling to go to space, and we found out that we need a 10-watt emitter with a M squared of 1.5 in order to do 1,000-mile LEO link to LEO link, and we know we can do that, and we're in the process right now of designing that. So that link would probably go tens of miles for a long distance, but we really see this as a unique way to do short distance links, even less than a mile, to many different connections to houses and businesses instead of 5G millimeter wave.
Thank you.
Thank you.